Welcome. In this video, we'll take a look at verifying or proving trigonometric identities. So this is a little bit different than just simplifying the expression. In these trigonometric identities, we would like to choose one side of our identity, or this equation, and manipulate it to match the other side. And generally, we want to start with the more complex side. We're only manipulating one side, and we want to make it match the other side. So let's consider our first example, number 8. We have the sine t to the fourth minus cosine t to the fourth is equal to sine squared t minus cosine squared t. So one thing that we can identify right away is the more complex side seems to be the one with the fourth powers. So let's consider using this left side first, and we're going to try to start to manipulate that side going down. So when I consider sine to the fourth minus cosine to the fourth, this is really a hidden difference of squares. If I consider this function, I can rewrite this in a clever way. Sine squared t, quantity squared, minus cosine squared t, quantity squared. So notice that this left side here is a perfect square, or a difference of perfect squares. So when I consider the factoring of perfect squares, just in general, we have, if we have a sum x squared minus y squared in general, we know we can factor this as x plus y times x minus y. And we'll want to use this technique here to factor this perfect square combination, where my x and my y are sine of t squared and cosine of t squared. So again, these are playing the role of x and y in this general expression. So when I rewrite this factor on the left side, I can say this is going to be sine squared t plus cosine squared t, that's the x plus y, and we're going to multiply that with x, which is the sine squared t again, minus cosine squared t. And again, our goal here is for this left side that we're manipulating to look like our right side here. So we're really close. All that we need to recognize here is that our first product that we just created has a Pythagorean theorem identity. Sine squared t, cosine squared t added together will just give us 1 times the sine squared t minus the cosine squared t. And this is exactly what we wanted it to be equal to. Again, multiplying by 1, we don't need that 1 there. If this is equal to 1 here. So this left side is, in fact, equal to the right side expression. And so we have verified this identity, and we can move on from this problem. So notice that I've only manipulated one side of this expression, and I've left the right side of that expression as is. And I just want to match that left side with the right. So let's take a look at another identity on number 9 and see if we can work our way through this one. So we have a 1 plus secant squared x divided by 1 plus tangent squared of x is equal to 1 plus cosine squared x. So it looks like we're going to be using some Pythagorean theorem identities along the way here. And in fact, the denominator here, we'll notice 1 plus tangent squared x. This is going to give us a secant squared x if we looked at our Pythagorean theorem identities. So we know that exactly 1 plus tangent squared x is equal to secant squared x. That's one of the Pythagorean theorem identities, so we'll use it right off the bat. And again, all I want to be doing is manipulating this left side in this case. All right, now we can consider splitting our function here into two parts. We can say this is 1 over secant squared x plus secant squared x divided by secant squared x. So splitting that fraction into two with the sum. And we'll notice that these two pieces we can also represent as sines and cosines here. The 1 over secant squared is just cosine squared x. And then plus secant squared over secant squared is just going to give us 1. And this is exactly what we wanted that left side to be equal to, 1 plus cosine squared x or cosine squared x plus 1. Either way, that is the same function on the right side. So in this case, again, we use the Pythagorean theorem identity that we listed here, and then splitting up fractions and using reciprocals. So it doesn't matter necessarily which side you start on, but it is, again, a good idea to start on the more complex side and to simplify the expression to look like the right side. So let's continue with a few more examples here. We'll take a look at number 10 together. So in this identity, we don't necessarily have any squareds right away here, or squared sines or cosines. So it might be a good idea to get a common denominator here with our fractions and see what happens. So if we start by getting a common denominator to start, I want to be able to multiply the first fraction by 1 minus cosine x, and the second fraction by sine of x. So let's consider what we're going to get here. We have 1 minus cosine of x. Well, that's going to be 1 minus cosine of x times itself, or we'll square that. And then plus, we'll have sine times sine, which is a sine squared x. And then this will be over one single common denominator. We'll call this just sine of x times 1 minus cosine of x. And again, I'm going to leave this left side here, and I'm going to try to replicate it with what I have started here. Okay, so I have a little bit of a problem to work out here. I want to square or FOIL out the 1 minus cosine x quantity squared. So let's do that first and see where that takes us. If I square this, it'll be 1, and then minus 2 cosine x will be my cross term, and then if I take the product, minus cosine times minus cosine, we'll get cosine squared x. So this will be that first expression squared out. And again, we'll have a plus sine squared x to boot on the end, divided by that same denominator of sines of x, and then 1 minus cosine of x. So let's see what we can do with our numerator here. I know I have a Pythagorean theorem identity sitting here. Cosine squared plus sine squared we know is equal to 1. So that's a nice identity we can use right off the bat. If we continue here, let's rewrite the expression we have. We'll have 1 plus 1. These will be 2, and then we'll have minus 2 cosine x divided by the sine x and the 1 minus cosine x. Notice that the 2 in the numerator here, we can distribute this out to give us the following expression: 2, 1 minus cosine x, and then we'll have sine x, and then 1 minus cosine x. This is looking really good because these two items can cancel each other out. So these 1 minus cosines cancel out, and I'm left with 2 sine of x, which, if we take the reciprocal there, is the equivalent to 2 cosecant x. And that is the expression we wanted to end with. Looking up there, 2 cosecant of x, and we have completed the verification of this expression. So in this, notice that we used common denominators for our fractions. We did some multiplication. We used our Pythagorean theorem once again, and then did some cancellations with some factors as well. So again, with these types of verifications, we're always thinking kind of problem solving in terms of using all of our resources. We're trying to use all of those identities to our advantage. And we want to consider, again, getting them in terms of sines and cosines when we're able to be able to finish off the expressions. So hopefully this is helpful, and we'll take a look at one more video with the identities. Thanks for watching.